Imagine we're playing a game where we roll dice. In each turn we roll a die. If we roll a 6, the game ends. However, if we roll any other number, we just roll again. When the game ends, we will win an amount of money corresponding to how many dice we rolled in total. Is there a way for us to find out how much money we are expected to win during our game? First of all, some basic facts about the game we are playing. There's a 5/6 chance we don't roll a 6, and the game continues, and a 1/6 chance we do roll a 6 and our game ends. To help us figure out our problem, we can use a very simple Markov chain to visualize the process. And now let's take a look at one and see how it can help us. So looking at our Markov chain, we start off at the roll again position. Then if we roll anything other than a 6, we roll again. And if we roll a 6, we move to the end game position. Looking at a game that ends in 2 rolls, we roll again once before rolling a 6. However, looking at a game that ends in 3 turns, first we fail to roll a 6, then we fail to roll a 6 again, before finally rolling a 6 on our 3rd roll. Let's define EN as the expected value only looking at games that end in N turns. First, we have to repeat the roll again step N-1 times, as there's a 5/6 chance of this happening on each step, and we need the first N-1 turns to not be a 6. There's a 5/6 to the N-1 chance of this happening. While on our last turn, we have to roll a 6, which there's a 1/6 chance of happening. Finally, we multiply by N dollars, as when we win the game on the nth turn, we win N dollars. And multiplying these all together gets us our closed form solution. But how does this help us? We can add up all of the expected values from 1 to infinity to get our expected value for the whole game. But how can we do this? Adding infinite values may seem daunting, so let's look at the partial sums to see if we can notice anything. As we can see from the partial sum of the first 50 values, it seems to converge to 6. Why is this, and can we find a pattern that generalizes to other p-values? Let's introduce the geometric distribution, which our dice game falls under. In a geometric distribution, we run some trials that succeed with a probability of p, and fail with a probability of 1 minus p. In our dice game, succeeding would be rolling a 6 with probability 1/6, while failure would be rolling a number 1 through 5, probability 1 minus 1/6. And we stop the trials once we get a successful result. So our question here is, how many trials do we expect for it to take for us to succeed? Let's look at p-values other than 1/6. For example, 1/10. From the first 100 partial sums, it seems to converge to 10. Based on the 2 probabilities we looked at, we can hypothesize that the expected value converges to 1/p. However, let's try to prove this. Our friend the Markov chain from earlier will come in very handy here. Let's analyze the structure of the Markov chain. It follows a recursive structure, where if we roll a die and we fail, we end up at the exact same spot. Also, our expected number of turns is the same, however, it's increased by 1. So we can view the expected value of the game as the sum of 2 things. Either we win with a probability of p, or we don't win with a probability of 1 minus p, and we're essentially still at the beginning, however all of the values have been increased by 1. And let's algebraically try to solve this here. We can expand the product of the yellow and the blue terms. The p and the negative p cancel out. We move the p ex over to the left. We can cancel out the ex on both sides. And finally, we divide both sides by p and get our final answer. Now we know that the expected value for the number of trials we need for a success with a geometric distribution is 1/p, and we can look at some interesting applications of this. Here we're given a binary array, which is to say an array of 0s and 1s, and every second we perform an operation on the array, where we randomly select 2 elements, such that I is less than j, and in this random selection every pair has an equal chance of being selected. If the second element is less than the first element, then we swap them. Let's take a look at how these operations look in practice. In this example, the randomly selected elements were at indices 3 and 4, and the value at index 3 is greater than the one at index 4, so our swap here is successful. When the elements 2 and 8 are selected, our swap fails as the first value is less than the second one. Finally, the two elements here are equal, so the swap fails. So now that we know how these operations work, how can we find the expected number of operations to sort the array, and how will the geometric distribution from earlier help us towards that goal? Finally, we can get to our solution. Let's compare the original array to the sorted array we want to achieve. In the sorted array, all the ones are in the target range. Let's see what happens when we swap the first two elements of the array. It's a valid swap, however, it's useless to us as no new elements entered our target range. How can we know what elements actually result in a swap that's useful to us? We can look at how many ones there are that need to be moved to the target area, and how many spots there are in the target area where they can be moved. Note this number is always equal because there are k ones not in the target area, which means there are k zeros that are taking up their spot. In our example, there are 3 ones to be moved, and 3 spots where they can be moved. So there are 9 total combinations that will move us closer towards our sorted array. Note that there are 9 elements in the array, so there's 9 choose 2 possible pairs that we can choose. So each turn we have a 9/45 chance of selecting a good pair. What is the expected number of turns for this to happen? Let's remember the dice game from earlier. As our problem fits the conditions of the geometric distribution, we know we can expect to select a good pair in 1/p turns, which would be 45/9 turns, which is just 5 turns when we simplify it. So after a swap happens, we're left with 2 ones that need to be moved and 2 zeros that need to be replaced. Therefore, the probability of getting a good pair is 4/45, and we can expect this to happen in 45/4 turns on average. And can you figure out what happens with only one more successful swap needed? There's only one pair that will lead to the array being sorted, and so we can expect this to take 45 turns. After this, the array is completely sorted, and we can sum up all of these times to get the expected value for the entire array, which in this case would be 241/4 turns, which is 60.25 turns. And it's nice that we've solved it for this specific array, but how can we solve this problem for any array? Let's examine the code for the solution. First, we have to find the number of ones present in our array of size n, which we define as num1. So in our sorted array, the last num1 elements have to be 1s. So let's try to find out how many zeros exist in those last num1 elements to find how many elements we have to swap out. In this array, we have 5 ones, and only 2 out of the last 5 elements are 1s. Therefore, we need to fill in 3 spots to sort the array. In an array of n elements, there are n choose 2 possible ways to select a pair of unordered elements, which is n times n minus 1/2. In this case, we have 9 elements, so n choose 2 would be equal to 45. At the beginning, the number of elements we need to replace is equal to the variable spots to fill, which we defined earlier. After we have a successful swap, it goes down to spots to fill minus 1, and this keeps going down one by one until we have 0 spots to fill and the array is sorted. Now we can calculate the expected value of turns it takes to reach I minus 1 elements out of place when we have I elements out of place. We have I ones not at the end and I zeros to replace. So we have I times I, which is equal to I squared possible good pairs out of the n choose 2 elements to replace. With our geometric distribution from earlier, we expect to perform a useful swap in 1/I squared over n choose 2 turns, which just simplifies to n choose 2 I squared turns, which we can repeat this process for all I values between 1 and the number of spots we have to fill, and the summation of this brings us our answer. I hope this problem was fun and interesting and that we can learn a lesson from this problem. If we have a difficult task we can't solve, it can be useful to break it down into something we can solve and then build off of that to reach our final solution. Let's end this with a follow-up problem. You're given a binary array of size 2n, and the first n elements are 1s and the last n are 0s. The operations in the original problem: what is the probability you will sort the array in the first n operations? Thanks for watching, and remember to like and subscribe only if you enjoyed the video, and I hope all of you learned something new today.